Professor Kарлos Herdeyro from the University of Aveiro, Portugal, and I'm going to say a couple of words about Carlos. He graduated in physics from the Faculty of Sciences of the University of Porto in 1996, and then completed his PhD at the University of Cambridge in 2001. And after that, he did postdoctoral studies at Stanford University, the United States, and at the University of Porto, right?
Yeah.
Okay, and then he became an assistant professor at the University of Aveiro, where he established a research group on general relativity. Currently, Carlos is a full professor at the University of Aveiro and head of the gravity group there. His research is focused on black holes and other compact objects like boson stars, rocket stars, and their dynamics. He's an author of more than 200 papers. It's worth mentioning that the Aveiro group is one of the leading groups in the world in the field of black holes, with scalar here, boson stars, rocket stars, and their dynamics. So I'm very glad that Carlos accepted my invitation. He is here. So Carlos, the stage is yours.
Thank you so much, Stoicho. It's a really great pleasure to be here. I'd like to start by thanking Stoicho and the whole group for hosting me. And today I've decided to talk to you about the landscape and surprises of compact objects with bosonic fields and general relativity. This topic has, as any topic, many perspectives. I will not talk so much about phenomenology or observational potential implications. I'm happy to discuss it. I'll talk more about the space of solutions, including their dynamics. So, and I would like to start by telling you that when you look at a certain subject, let's say compact objects, you typically look at it based on a certain paradigm in which you are educated. That's for some reason, of course, and typically it's a good reason, but that develops a sort of a tunnel vision, in the sense that you think about it in a certain way, but you don't realize that if you twist a little bit the ingredients, then you might have something slightly different, or very different. Because our understanding of any subject, in particular the most compact objects in the universe, and in particular black holes, is based, in this case, on a certain model, but you can also think it's biased by that model. So let me be concrete. So when you start studying general relativity, you learn about black holes in Einstein-Maxwell theory. That is just the theory that has the Einstein kind of field equations coupled, minimally coupled, to electromagnetic fields. This is for a good reason, of course. And the theory is quite interesting, in particular when you try to calculate the simplest solutions, which are axisymmetric and stationary, because you want something in equilibrium. There's a very, these solutions are known analytically, they are very nice. You can write them on a line in a piece of paper. And the theory is actually integrable, in the sense that with enough symmetries, this model, Einstein's theory, can be cast as a nonlinear sigma model, and you can use many techniques that you know to derive even more complicated solutions. Also, in this model, it's known that there are no solitons, meaning if you ask yourself, could I have a bunch of gravitational waves or electromagnetic waves that under their own weight they would form a sort of soliton, a stationary kind of bundle of energy that would be localized, asymptotically flat, that would have no horizon, unlike black holes, be everywhere regular? And the answer, no, you cannot have these particle-like models in Einstein-Maxwell. The compact objects are black holes, they have a horizon. And the black holes are simple in a sense. There's a bunch of uniqueness theorems, and Stoicho is one of the experts on these, that tell us that the unique solution of a black hole is described by only a few macroscopic parameters: the mass, the angular momentum, and potentially the electric and magnetic charges, although these ones are astrophysically thought to be not so relevant. And so black holes are said to have no hair, where hair is a metaphor for more complexity, another set of degrees of freedom, macroscopic ones. And perhaps of a more academic interest, you could ask, could I have two black holes in equilibrium? Well, this sounds a bit weird because gravity is attractive. That's what we are taught when we learn Newtonian mechanics. But in general relativity, gravity can also be repulsive. And for instance, if you have the spin-spin effect of two black holes creates a repulsive part of gravity. So you could ask, could I have two black holes that they are being attracted by their weight, but also their spin is actually balancing them? And the answer is no. There are no balance neutral two black holes, although there are actually solutions describing extremal black holes, which means they have electric charge and as much electric charge as they can have. And those ones can actually exist. This is true if instead of one Maxwell field, which is what appears to be in the real world, but if you go to more complex physics, sometimes you have more than one Maxwell field. If you have multi-Maxwell fields, this is still true. In particular, it's true if you have two and you cast them as a complex Maxwell field. But if you do a tiny, or apparently tiny change, which is to give a master to this complex Maxwell field, then you have what's an Einstein complex Proca field, theory, or Einstein massive complex Maxwell. And in terms of these properties, that's very similar to what happens if instead of the complex massive vector, you have a complex massive scalar. So the theory with Einstein, massive complex Klein order. This could have self-interactions, but let's take the simplest model. It does. So the addition of this master changes quite a lot these properties. And for instance, the downside is mathematical because the master creates an obstacle to the integrability structure. So, and that means also that even in the simplest cases, say in spherical symmetry, if you try to calculate the simplest models of compact objects where these bosonic fields, the vector or the scalar, are excited, you actually can only find them numerically. There are no nice closed form analytic solutions. But the upside is physical. Now there's a very rich landscape of solitonic solutions, and these are called bosonic stars, and that's what I'll tell you with that. And they have rich dynamics and sometimes dynamical surprises, and I'll tell you about one of these dynamical surprises today. And moreover, because of the existence of these solitons, in some cases you can actually put the black hole horizon in equilibrium with this kind of solitonic environment, and you get the new class of black hole solutions. And these are black holes with synchronized bosonic hair, which has a deep relation both to these bosonic stars and also to the phenomenon of superradiance, which is a very interesting phenomenon, which is not exclusive of strong gravity. It appears in many contexts in physics. It's the energy extraction and angular momentum, in this case, from a system mediated by, in this case, the bosonic field. And again, perhaps more of academic interest, you can also construct, because of this environment of these bosonic fields, two black holes being in equilibrium in which this gravitational attraction can be compensated by a bosonic repulsive interaction. And I'll tell you briefly about this today. So my point is, this simple change, if you have a, instead of just a Maxwell field, if you have a Maxwell field but with a master, or a scalar field complex, well, with a master, then you get very different things. And this is all general relativity. I'm not talking about modified gravity here. So today I'll focus on these three topics, briefly, mostly on this, a little bit on this, and briefly on that, to tell you and illustrate these differences. Okay. So let me start with the landscape of solitons and tell you about these bosonic stars and some dynamical surprises. I should say that this is work done with many people that I've kind of put on the first slide, and some of it is not yet published, and in particular one of the things I'll tell you, which I found very interesting. Okay, so what are bosonic stars? Now, you can give a kind of macroscopic perspective to this. So they appear in general relativity with simple and physically reasonable matter sources, just a complex massive scalar field or a vector field. They could have self-interactions, but certainly with a master. So these two models that I've written here, this is just the Einstein complex massive Klein-Gordon action. There's a minimal coupling, as you can see here, very simple model. And this is massive complex vector vacuum, if you'd like. This is just a complex vector field with a master, minimal coupled to Einstein's gravity. So these solutions describing these stars, so lumps of energy, I'll tell you more about it, they appear here and they are called scalar boson stars, or here they are called vector boson stars, also known as Procus stars. And these are by no means exhaustive. You can also find these things in modified gravity. You could have non-minimal couplings between these bosonic fields and curvature. You could have self-interactions. You could also have higher curvature terms, and these sort of solutions exist as well. But let's take this as our simplest models, in which there is this master that's fundamental that will determine the maximal mass of these stars. And this can be faced as a new scale. You can think about as the inverse Compton wavelength. This has the inverse Compton wavelength, and the Compton wavelength, depending on the mass that you choose here, is determining a new scale in which different physics could happen. And this will be our reference models, but again, you could have more complicated models. But these objects can also have a microscopic perspective. They are often described as Bose-Einstein condensates of many ultralight particles, and I'll tell you why they are ultralight in a bit, in the same quantum state. And the fact that there are many justifies the classical description. If you calculate the action, it's much, much bigger than h bar, so the classical description is okay, although you are talking about some sort of Bose-Einstein condensate. And the need for ultralightness comes from the existence of a model-dependent maximal mass. You'll see that in a bit. So, and this maximal mass for the stars that you can create depends on the mass that you choose for your bosonic field in your action. And it scales like this, it turns out. So there's 10 to the minus 19 solar masses. There's a constant here of order unity. This is determined by finding the solutions. And then there's the inverse of the mass of the bosonic particle in GeV. So if you would like these bosonic stars to have masses in the astrophysical black hole mass range, so we know black holes, and we know them from about 1 solar mass to about 10 to the 10 solar masses. And if you'd like these objects to be in the same mass range so that they could mimic black holes, for instance, and perhaps, mimic the signals that we think are coming from black holes, and we can inquire if they are really black holes or other objects, then this bosonic field mass should be in this ultralight range, 10 to the minus 10 to 10 to the minus 20. Now this is very ultralight as compared to typical standard model masses, and if such hypothetical particles have feeble or no interactions with standard model constituents, they should have something related to the Higgs particle, but no other kind of couplings. They are called fuzzy dark matter, which is one of the models that people have been mostly interested in the last few decades as a potential candidate to describe the dark matter, and therefore only detectable gravitationally, but almost impossible to detect in particle colliders unless some other channels of decay, and that is very model dependent. Of course, you can ask, and you should ask, how can you have such ultralight masses and be protected about all sorts of quantum corrections? And people have put forward scenarios. Unfortunately, this was a bit cut, but that's okay. So there's one scenario that is called the string axiverse to try to provide a high-energy physics origin for such ultralight bosons. And this comes from string theory constructions, but there's more mundane, I would say, constructions in which are extensions of the standard model that don't require such exotic ingredients as the string axiverse. And that you could get these sort of particles and perhaps some interesting accelerator phenomenology. Right, so let me tell you a little bit more about these bosonic stars. And I want to get to the issue of stability and their dynamics. Now, the simplest models are spherical stars. always you start with the simplest thing when you want to study a star, although, you know, rotating stars are kind of the most common objects in the universe, not spherical ones, but let's start with the spherical stars. And for calculating this in general relativity, you give an ansatz to your bosonic field, either the scalar or the program. Now, the important thing in order to circumvent Dirac-type theorems, if you know about this in classical field theory, is to have this harmonic time dependence. So, because the field is complex, this vanishes at the level of the energy momentum tensor, and it's compatible with the geometry and metric that's fully time independent. So, you know, all physical quantities are there, but the amplitude is oscillating. And this is very much like stationary states in quantum mechanics, if you think about it, in which you have an amplitude that oscillates, but then your probability density is fixed. That's why it's a stationary state. So that's, again, a relation with this being thought as some sort of macroscopic quantum state. So there's this frequency here, and this frequency actually is what determines the mass of the star. So in these plots here, for the scalar and for the vector case, I've plotted this red solid line, which is the ADM mass, so the physical total mass of the star, in terms of the frequency that appears there. And there's a typical curve that does some spiraling around, and the same for the vector. So it's the red curve here that matters. And it turns out, by studying spherical perturbations, that there is an unstable mode that emerges here at the maximum of the ADM mass. So there's a transition instability. Solutions here don't show any instability against radial perturbations. But solutions beyond this point, they are unstable against radial perturbation. And studying the evolution of the solutions here in the unstable branch, there are several different fates that people have looked at. They can migrate, they can become black holes, or they can simply disperse entirely. So this has been thought to be a stable branch, and this description has been thought to be parallel for the scalar and the vector case. And this has been common knowledge for some time now, although the vector case has been found much more recently than the scalar case that has been known for 50 years. And this conclusion that there is a stable branch has been reinforced by two other kind of pieces of evidence. The first one is you can actually form these stars. So if these stars were to exist in the universe, well, first of all, this kind of bosonic field would have to exist, and we haven't seen it, but we don't know what dark matter is, so, okay, this is a possibility, let's say. And, okay, but would they form dynamically then? And people for some time have been putting effort in trying to come up with scenarios, because we know how stars form, collapsing of a gas cloud and so on. So do these stars form somehow? And indeed they can, as shown by numerical simulations. So you start with a dilute kind of distribution of one of these bosonic fields. This is in spherical symmetry, and with some Gaussian distribution. And then the field collapses under its own weight. And there's a mechanism to eject the excess of kinetic energy so that the compact object can virialize, and you can form something that's compact. So for stars, usual stars, there's radiation. Here, there's no radiation. And this mechanism has been called gravitational cooling. So as the star kind of becomes more compact, there's ejection of high velocity jets, if you'd like, of bosonic field that carry the excess kinetic energy so that you can create a compact object. And this has been done for the scalar case. This is the classical illustration by these people, Seidel and Swen, but also repeated for the vector case more recently. And you can even start with more mass than the mass limit, the maximal mass of the model. And you can see that indeed the excess energy, this mechanism of gravitational cooling, can get rid of this excess energy, and therefore you could create a star, which is an equilibrium state. Although, of course, in these simulations, you never get there. There's always kind of a state that's oscillating around some equilibrium state. And because of this kind of putative stability of these lumps of this bosonic matter, self-gravitating, people have actually started to do numerical evolutions of collisions, of binaries, to get gravitational waveforms that you can compare with the LIGO, Virgo, Cairo templates, so that you could assess if what we are seeing there is better described by black holes or by something like this. And actually, in some events, there's some interesting possibility that these models fit slightly better what we are seeing. And for instance, here it's a collision of two Procus stars. They are given a slight transverse momentum, so it's not a head-on collision. They gain a little bit of orbital dynamics, but not too much. And then, because of doing this, people have seen that they collide. You can form a hypermassive Procus star, or you could form a black hole, depending on the initial conditions and so on. But nothing strange is going on here in these initial dynamics about individual stars. So you kind of think that everything seems to agree that these spherical stars, in the right branch, they are stable, both for the scalar case and for the vector case. But it turns out that they are not, and this is a kind of interesting result I would like to tell you about today. The spherical mini Procus stars, just ones in the vector case, they turn out not to be stable against non-spherical perturbations. So they are stable against spherical perturbations, but they are not stable against non-spherical. And before I go into detailing that, let me tell you a little bit of an history about the scalar case. Okay, so I'll go to the scalar case. Some time ago, together with some people in Germany and other collaborators, actually Prapeshko was in Belarus and Schnir was in Russia, and we've shown that these bosonic stars can have a multipolar distribution. You see, if they are sort of Bose-Einstein condensates, somehow they are macroscopic quantum states, orbitals. It could be that, like orbitals, they also can have, multipolar structures, and they can. So, in order to understand this construction here is for the scalar case, I will give you the following kind of understanding. Consider the Klein-Gordon equation on flat spacetime. This is the massive, free Klein-Gordon equation, and you try to solve it. It's a kind of undergraduate exercise. And you can find a solution such as this. So there's a harmonic time dependence here. And then there is a real spherical harmonic, depending on L and M, quantum numbers. And there is a radial profile, which is defined by a modified Bessel function of the first kind, which has this form here. Now, this radial function actually is diverging at the origin, and therefore this solution is not regular. But if you couple it to gravity, minimally couple it, gravity regularizes. And the nonlinear continuations, because the theory of gravity is nonlinear, it's Einstein's general relativity, the nonlinear continuation of these solutions when you turn on gravity are these structures here, which are bosonic stars with a multipolar structure. Of course, because of the nonlinear structure, you'll turn on more of these guys, spherical harmonics, but asymptotically there's going to be a linear. So these two last numbers that you see here in this trio are actually the L and the M. And therefore, this here is the monopolar star. It's just a spherical star, which is like your basic orbital, 1s, if you like. Then there is a dipolar one, which is dominated by a Y 1, 0, if you like, spherical harmonic. And this is a quadrupolar one. And you can build this analogy to a large extent. And there is a kind of a cunning morphological analogy with what you know from your orbitals in hydrogen. And as you know from your orbitals in hydrogen, as you go up in quantum numbers, the energy goes up. And this is, to a large extent, true here. Meaning, well, for the spherical, the monopolar stars, you have a certain mass, which has a certain range depending on this frequency. So the difference with the orbitals is that energy quantization gives you, for each choice of your spherical harmonic, and if you fix the number of radial nodes as well, a single frequency, energy quantization. Here, there's a range of frequencies. There's a range of frequencies in which solutions are possible. So for the spherical stars, this is the energies or masses, for the dipole and for the quadrupole. But if you fix your frequency, you see that as you go up in these quantum numbers, the energy mass is going up. This is more or less what you expect. And with these adaptations, this is what happens. So when we tried to do the same thing for the vector case, we found something that was surprising. So now we are talking about the vector case, the Proca case. So we found that when we looked at the monopolar, that is the spherical stars, that the mass, their energy, depending on the frequency, follows this black solid dashed curve. Okay, fine. Then we looked at what are the dipolar stars here, which in this case turn out to have a prolate energy distribution. And very surprisingly, their mass turned out to be given by this blue curve here. Why is that surprising? Well, because in the would-be stable branch for the monopolar stars, the spherical stars, it seems that the dipolar stars have less energy for the same frequency. And that was not to be expected. That's strange, we thought. And actually, if you go to the quadrupolar ones, then you have this red solid curve here. And it turns out that even here, for the quadrupoles, they have less energy for the same frequency as the monopole ones in a given kind of frequency range. So we thought, well, is this telling us that actually the ground state of this model is not the spherical star, but rather a dipolar star? It's kind of, we thought, well, that's kind of suspicious because we weren't thinking this was possible, and this was certainly not the case in the scalar case. So we kept digging and looked for something else. And turns out that there is a second piece of evidence that was convincing us that indeed the dipolar stars, which are prolate in the vector case, are actually the ground state. And this is related to morphology. And this, for this I will invoke again your knowledge of basic quantum mechanics and remind you that, well, look only at the spherical orbitals in hydrogen. Then you have 1s, 2s, 3s, 4s, so on. And the distinction between them, or one of the distinctions, is the number of radial nodes, isn't it? It's just that, because it's the same spherical harmonic. And the higher the number of radial nodes, then the higher the energy. It's an excited state. So there's also excited states here for these bosonic stars. Besides the multipolar structure, you can also give a number of radial nodes, which means that the energy distribution has a shell structure. So for instance, this is a model for spherical scalar stars. This is actually a model with self-interactions, but it's the same in the simplest model, the reference model. And this is the mass for the solutions with no radial nodes. This n denotes the number of radial nodes in the scalar field profile. And then this is 1, 2, 3, 4, 5, and up to n. And you see the energy goes up. When we first looked at the vector stars, they were calculated in general relativity, minimally coupled to this massive complex vector using this ansatz. I've shown you this part before. This is the metric ansatz. And when you look at one of the equations of motion that comes from this, one of the Proca equations of motion, which is this one, well, you can do a very simple calculation, integrate this over the whole space from 0 to infinity radially. And it turns out that this term here is just a boundary term, and you use the boundary behavior of the functions in order to have regularity at the origin and asymptotically flat. And this just vanishes, which amounts to the fact that then this integral here of that side from 0 to infinity is 0. But you see, these functions here, sigma n, which are here in the metric, they cannot have zeros and they are positive. So it means that in order for this to be 0, f has to change sign. And that means that the scalar, we call the time component, the scalar component of the Proca potential has to have at least one node. So the vector stars had to have at least one node. And this was a bit surprising as compared to the scalar case. Because in the scalar case, you have that the basic fundamental solution has no nodes. And, well, so we thought maybe that's the way it is, and that's life. And actually that led to some confusion I'll tell you about. But actually there was a missing link, which we missed at the time. And the missing link is that there are indeed these prolate stars. And these prolate stars are again the true fundamental state, and they have no nodes. In order to see that, you have to calculate them, and this is a bit more complicated because now you are not in spherical symmetry. So you have to have an ansatz for your fields that depends both on the radial and the theta copolar coordinate. And you have to excite more components of this vector field here, this Proca potential. So if you do calculate the solutions, which as I've said are prolate, and you look at these components here, for instance, the V, the scalar potential, and this H1. These are just convenient ways of writing, and the same would be true for the H2. And you look at them, and these are the curves for fixed theta. So now you have to look at each theta. So theta equals 0 up to theta equals pi over 2. And they never cross the axis. So there are no nodes. So these solutions not only have less energy, less mass, but morphologically, they seem to be the sort that is the ground state. They have no. But of course, the true discriminator is always dynamics. You have to do dynamics and see what's going on. So, because we have a machinery to actually do fully nonlinear numerical evolutions of the Einstein bosonic equations, using 3D numerical relativity simulations, developed, for instance, in this paper here, we ask the number of questions, and we've evolved these solutions using the equilibrium solutions as initial data to see what's going on. So here's the first question we ask. Now, if these dipolar Proca stars are the ground state, are they stable in long-term numerical evolution? So you put them in the computer, one of these prolate stars, and let it evolve, just with the noise from the truncation error. What happens? Okay, for that we've chosen a number of illustrative solutions, say from 1 to 4 here. So these are the prolate stars, the ones that are the candidates for the ground state. And we've evolved them. So I'll show you a couple of movies here. So the left-hand side is the imaginary part of the scalar potential, so the temporal component of the Proca potential. And the right-hand side is the energy density. So there you go. These evolutions run up to 20,000 in code units, which means approximately the light crossing time. So they are fairly long. And what you see is that here on the left-hand side, you see some phase dynamics, simply because of there's this harmonic time dependence, and sometimes you get it in different phases. But this is just phase dynamics. In terms of the energy density, the distribution, the physical quantities, it's unchanged. So at least in this time scale, these prolate kind of rugby balls, although kind of fun, they seem to be there. They don't do much. They like to be there. They don't decay. Fine. Okay, so then let's ask the second question. Well, if the dipolar Proca stars are the ground state, are the spherical stars unstable? Now, typically we think about the spherical states as being the ground state, okay? So what happens to the ground state? So again, we go to our space of solutions, which is the black solid dashed line, and we choose solutions 5, 6, 7, and 8. And we've evolved them, and I'll show you here, this is solution number 7. And you can see now that things are spherical, unlike the other case, it was prolate. So what happens? So you evolve this, and after a little bit, actually things start to change. So I'll show you again. When it gets to a time scale of about 2000, the spherical symmetry is lost. You clearly see that there seems to be a dipolar structure emerging, but there's also a kick. A kick is something that you see, well, in, for instance, collisions of black holes. There's some famous examples, and that's because there is an asymmetric emission of either gravitational radiation or some other component that could explain. There's a recoil. There's a recoil. So what happens here is that when you are moving from the spherical star, which is even in terms of the Broca field, the north and the south are the same, and you're moving into something which is odd, because for the prolate stars, the north and the south change by a sign, you actually trigger a momentum turn in the metric. And this carries some momentum, which gives a recoil to the star. So we see this in all of the evolutions. So this is telling us that our spherical star, which we put there, doesn't want to stand still. It wants to evolve into something else. Indeed, it doesn't seem to be stable. And then we try to play a little bit, okay, let's try to force it to stay there. So let's do the following, which people do a lot in numerical evolutions. You want to save computational resources. So instead of evolving the whole space, the 3D space, you impose artificial symmetries. So for instance, you can impose, let north and south be the same. And you only involve the north, putting appropriate boundary conditions. You see, if you do this in this case, you could kill the instability in principle, because the endpoint of the instability, assuming it is indeed the prolate stars, they are Z2 off. So if you are imposing that the north and the south have to be the same for all fields, then the north and the south cannot have a different side for the Broca field. So we try to do this, and something funny happens, which is the star still doesn't want to stay spherical. It goes into another state, which is Z2 even, which is the quadrupolar state. Now, the quadrupolar state has a dynamics both in this direction and in this direction. And after a while, actually the quadrupole decays into the prolate state, but now the prolate is oriented like this, so that it can actually obey the symmetries that we impose. So it does seem that the spherical stars are simply not stable, which is surprising. And now let's ask a final question. So let's go back to that formation scenario. I've told you that these stars could form, but all those evolutions were done imposing spherical symmetry. Let's then revisit the formation scenario in which you start with this Broca field dilute, like a gas cloud, and it would collapse under its own weight, but now we don't impose any symmetry. And see, this is what happens. It starts to collapse, but after a little bit, it actually loses its spherical shape. And you can clearly see a dipolar structure emerging, although in these evolutions you never get to an endpoint. It's still evolving. But it does show you that in the collapse, the spherical symmetry is not maintained if you allow a more generic dynamics, and that it seems to develop a dipolar structure. So this is a little bit surprising overall, again, because we are used to thinking about these spherical states in many physical systems as the ground state. And let me make some comments. In the case of strong gravity, this is curious because the prolateness rather than spherical symmetry of the ground state in this model, Einstein-Broca, gives an example of a static strong gravity system. And this can become quite strong gravity. It can reach compactnesses comparable to that of black holes. It's not spherical. So in vacuum general relativity, we know if you just impose staticity, it's Israel's theorem. The black holes in vacuum general relativity, they are spherical. So spherical is the preferred state. But here in this model, it wants to do something else. And the stability of the spherical Broca stars was missed in previous works because it was tacitly assumed, well, that if you just do perturbative radial stability, and if it survives that, it survives everything. Well, that's not true. And the numerical relativity simulations that were done before, they were either too short, or they were inadvertently imposing symmetries that were mitigating or even quenching the instability. So it's curious because, of course, you start by doing the simplest things, but then the extrapolation of conclusions is dangerous. And Now, if you're thinking, what's the basic physics behind all of this? I will not give you a final answer because I actually do not have a final answer, but I'll tell you the following. There are other interesting systems where spherical configuration decays into a non-spherical one. And the simplest one that you can find is probably a drop of liquid where you put charge, electric charge. There is a threshold limit in which it becomes unstable. And that was studied by Lord Rayleigh at the end of the 19th century. And it maybe has some similarities with some of the physics going on here, although, of course, there are also differences. Now, as I've said, but, stars in the universe, and, well, I'm giving the possibility that these things could be describing something in the universe. They are rotating. So what's the impact for the rotating stars? There's an interesting story. So, because in the original paper where these spherical protostars were calculated, it was proven mathematically, as I've shown you, that they have at least one node. Then the calculation of the rotating ones, which can be done as well, numerically using different techniques, the calculation revealed a family of these rotating protostars also with one node. You see, the number of nodes in these calculations is not something you put a priori. You're solving a bunch of PDEs, nonlinear, with some boundary conditions. And, for instance, to solve for the rotating solutions, use a Newton-Raphson method. It's a relaxation method. So you have to start with some initial guess. And then the kind of procedure finds a solution. It might find a solution with one node, or two nodes, or three nodes, depending on what you start with. And the solutions that were found actually had one node. And the authors, which includes me, at the time thought, well, that makes sense, because the spherical stars have one node, the rotating stars should have one node. So we found these solutions which have this morphology in terms of the energy distribution. They look like a Saturn, because there's a node. But for different reasons, then it was found a few years afterwards that there was a different family of rotating protostars which have no nodes. These are spheroidal, like the rotating Earth. And these have no nodes. And at the time it was thought, okay, well, it's life, because, well, the spherical stars have one node, but now the rotating stars don't have nodes. There's a family. Okay, go figure, but that's it. And this case of these protostars, which are rotating and which have no nodes, which are the fundamental state in the rotating case, actually are quite different from the scalar case, which turn out, and this has been known for many years, that are mass tori in general relativity. The scalar rotating stars have a toroidal energy distribution. And this difference in morphology, which is quite interesting, actually reflects itself also in a difference in dynamics. These stars here are unstable. The rotating scalar stars are unstable. And this was a bit of a surprising result found a few years back, because it was thought that the scalar rotating stars, they have no nodes, the minimal model, they were a kind of a ground state, and they were stable. They were dynamically robust, but they are not. And they develop a non-axisymmetric mode. So I'll show you here a little movie with an evolution of one of these stars. What happens is that at the moderately long time scale of the order of 1,000 light crossing times, this is looping the movie, by the way, and you see that there is a destruction of the spherical symmetry. So what you're seeing here is the energy density from above. This is like a donut, the star, and you're looking at it from above. And when the instability kicks in, what happens is that it decays into a black hole. We know that because we can find an apparent horizon. So as the mass goes into the apparent horizon, this is the scalar field, the mass of it just goes away. Some of it is dispersed. Most of it is actually swallowed by the black hole. And a black hole forms. So these stars decay into a black hole. But when we try to do the same, okay, let's now test the stability of the rotating protostars, which are the ones without nodes, the ones that we found that had no nodes. And we try to kind of force it as much. So for instance, here you put a very large perturbation on the protostar, such that it changes visibly its morphology. And here you start with an excited state, which is Saturn-like. And in both cases, what you can see is that the star doesn't, one, collapse into a black hole, and two, doesn't lose its angular momentum. it wants to keep, you know, a spheroidal lump of energy which is spinning, and it's kind of still doing something. It didn't get to a final state, but there's no evidence that it actually goes to something else rather than the fundamental spinning process. So these spinning protostars are dynamically more robust in the simplest models, and there's an interesting story about self-interactions, but I will not go into that. So, and I would like to finish this part of my talk by telling you the following. So it's kind of, as compared to Einstein-Maxwell, first of all, there are these solids, which doesn't happen in Einstein-Maxwell. But moreover, although at the level of the space of solutions, you find some similarity between the scalar and the vector model. There are spherical solutions, these monopoles. There are dipolar solutions, although here they have two lumps which are kind of separate, and here it's a prolate kind of distribution. There are spinning solutions. Here they are toroidal, here they are spheroidal. So there's still a similarity in the existence of solutions, but in terms of the dynamics, what survives is kind of different. So in the scalar case, the fundamental scalar spherical stars, they are dynamically robust. We have no evidence to think otherwise. But these dipoles decay, the toroidal spinning stars, they want to collapse into black holes. But in the vector case, it's actually the spherical case, the spherical stars that don't seem to, you know, be dynamically robust. And the dipole is preferred, and the spheroidal stars are actually dynamically robust. And this is a prolate model, this is a non-late model, which is kind of cute. So, how am I doing with time? Do I have time? Are they telling us to go out? Or because
You have 5 minutes.
I have 5 minutes?
Yeah.
Only? Oh, wow. So, I mean, there's a more complicated thing with stars. You can add more fields, do other things, but I will not discuss that because I want to tell you about black holes. So I think that there's an interesting story related to these stars and black holes, so I'll briefly go into that. Now, in these same models that I was discussing, so this is the same model, not only you have these bosonic stars, but it turns out that you can put a horizon inside one of these bosonic stars as long as they are both spinning with a particular synchronization condition, and you have new black hole solutions. Not only that, but these new black holes could arise dynamically. And they are interesting to the phenomenon of superradiance, but I will have no time to discuss that. And they could be particularly interesting for a description of supermassive black holes, and there's been new features in gravitational waves from memories, which are extreme mass ratio in spirals, such as a backpicture. I'm sorry, yes, sorry, it was your name here, but sorry about that. Not my fault, it's the projector. Anyway, so, but why are these called black holes with synchronized hair? So there's a nice piece of physics here, so let me tell you. So you might know that there are many physical systems and biological systems as well that achieve synchronization when appropriate couplings are at stake. So this is a video from fireflies in Thailand. And they are made to synchronize their flashes by putting some electrically controlled lamps, and they just synchronize with them. So in nature, you find examples of dynamical synchronization. Sometimes you look at them and you might think this is kind of odd. I look at these metronomes and they are in phase, and I think this is fine-tuning. Is it? Actually not. You can start with them with any phase that you'd like, but if you allow appropriate couplings, and here the coupling is just to put your metronomes on top of a platform, and you can put them on top of two cans so that they communicate. And you do not have to wait too long until they synchronize. So this is an example of dynamical synchronization. As I've said, you find it in the biological world in many instances, and the physical world as well. So let me give you a gravitational example now. You all know that the moon is showing the same face towards the Earth at all times. Is this fine-tuning? No, this is tidal locking. So the fact that the moon shows the same face towards the Earth was not an initial condition. It's just the fact that tides give rise to that effect. But the Earth is not showing the same phase towards the Moon, but it actually wants to do that. So the synchronization of orbital and rotational periods is a consequence of tidal interactions. So the Earth has a period of about 24 hours, the rotational period, which is much faster than the orbital period of the Moon. So the tidal bulge on the Earth, because of the Moon, actually leads, because it just goes ahead faster. And this creates a torque, and it slows down the Earth. But angular momentum is conserved, so the Moon goes away, and that's why the Moon is getting away from the Earth. But in the solar system, this is not always the case. You go to Mars, and there is Phoebus. Phoebus actually has a very fast orbital period, faster than Mars's day. So the tidal bulge that's created on Mars by Phoebus actually lags with respect to the position of Phoebus. And therefore, the torque is now to speed up the Mars's day. And what happens is that there's an inward tidal acceleration that makes Phoebus fall towards Mars. And there's an interesting case in the solar system because it's more like a double planet. Pluto and Charon have more or less the same mass. It's a factor of 2 only or something. And because of that, it has fully synchronized. So all the 3 frequencies are the same. So in the case of this model, for instance, there's these black holes that can exist, can be seen as a synchronization example. What does that mean in this case? Well, there's 2 angular velocities. This is kind of a metric ansatz for these type of black holes. And there's a condition under which the synchronized black holes exist, which is this one. Omega h is the value of this function here, which is the non-diagonal term, essentially, of the metric. And it's the angular velocity of the horizon. So the black hole is spinning, and the horizon has some angular velocity. And this here, you look at the scalar field, there's a phase, and there's a phase angular velocity, the frequency, and this is an integer. So the synchronization condition is that the velocity of the angular velocity of the horizon is the same as the phase angular velocity of your scalar field, the phase angular velocity. And so in a pictorial way, I mean, it's your black hole, which is kind of, horizon is illustrated in black here, is synchronized with this phase of the scalar field. And this can also be achieved dynamically via this phenomenon of superradiance. So a few years back, East and Pretorius looked at the Kerr black hole. Kerr black hole is just a spinning vacuum black hole, and you put a seed of this Proca field. In this case, it's for the Proca, it's for the scalar, but there exists. And what happens is that if this phase angular velocity of that mode of the Proca field is below the angular velocity of the horizon of the black hole, then the mode extracts energy, rotational energy and angular momentum from the black hole and grows. And this is the growth of the mass, which goes into now what people call a cloud or a hairy black hole. And it kind of saturates at some point. These are for different models. I will not explain. But the important thing is that the angular velocity of the black hole then decreases, and it basically meets the phase angular velocity of this dominating superradiant mode, which is this vector. So it's a synchronization. And at least from this end, this synchronization could occur. And the end point is a black hole with synchronized hair that we've identified in this paper. So these black holes are dynamically interesting. They could form. Now, there's a large parameter space, and there are many solutions that could be unstable. Some others could be stable. We are now doing numerical evolutions, and I'd just like to tell you, so this is an evolution of a hairy black hole of this. So there's this kind of toroidal, in the scalar case, cloud around it. And this is just the depiction of the phase of the scalar field, and the black hole is sitting there for as long as we've evolved them. So they are not decaying, they are not doing crazy things. So this cloud of bosonic field around the black hole seems to be robust. So with that, I think that I have to finish. I would like to tell you about this, but unfortunately we do not have time. The idea is that you could use also these ingredients, these bosonic stars and these black holes, to endow two black holes with this bosonic environment and balance them. And this was possible to be done, and it was actually published about a month ago in PRL in this paper. So I'll leave it as a teaser so that if you'd like to know more about it. Thanks so much, and I'm sorry if I extended a bit too much. Thanks.
Quick questions? Any question?
One simple question.
Yes, please, go ahead. Yes.
Are those bosonic stars completely homogeneous? I mean, because they're some sort of quantum state.
Right.
And, is there any structure inside, or they're just considered as a homogeneous?
Right. So if by a homogeneous you mean like the energy density is the same everywhere, no, it varies, right? So yeah. So for instance, the toroidal stars that I was telling you about, the spinning scalar stars at the very center, the energy density goes to 0, so then it increases, and then it goes down. The spherical stars, typically, they start with the maximum of the energy density at the center, and then they go down. So this has a kind of Yukawa type decay. So it only goes to 0 at infinity, really. But because it's exponential, then you consider the radius of the star where, say, 99% of the mass is, right? And this is, but this, you see, unlike, just a little point too, unlike, you know, when we evolve stars, real stars, there is a discontinuity of physical quantities at the surface. You see, because the star ends here. So physical quantities go to 0 here. There's a discontinuity in the pressures, whatever. And if you are doing something like a numerical evolution, dynamics, and so on, this creates difficulties. These models, in a sense, are simpler. Why? Because it's all smooth. It goes to 0 exponentially at infinity. Of course, your grid is not infinite and so on. But the fact that you don't have these discontinuities makes it more amenable to any sort of numerical treatment. That makes them interesting, at least as toy models, perhaps as something else, but at least as toy models.
Thank you.
Thank you.
Okay. Let us thank the speaker again.
Thank you. Thank you. Well, I'm sorry.